Hello everyone, welcome to my channel Math 6 IIT Academy. Now let us discuss about functions. Okay, so to define function, we need two non-empty sets. So let us consider A be non-empty set and B is another non-empty set. Function is a relation from one set to another set. That is, let f from A to B be a relation is said to be function if every element in set A has one and only one image in set B, then the relation f is called function. F is called function from A to B. Okay, so f from A to B, here both A and B are non-empty sets, and basically it is a relation, and this relation is said to be function if every element of A has one and only one image in set B, then the relation is called function. Let us see examples. I am taking A is equals to suppose 1, 2, 3, and I am taking B is equals to suppose A, B, C. Now here I am taking in terms of Venn diagrams. So this is the set A and this is set B, and I am defining the function f like this. So here A I am mapping with 1 is mapping with A, and 2 I am mapping with B, and 3 I am mapping with C. So here you can observe that every element of A have only one image in B. That means here with respect to 1, A is called the image of 1. That is, f of 1 is equals to A, f of 2 is equals to B, f of 3 is equal to C. The elements in first set are associated, are mapped with one and only one element of set B. So this is called a function. Now the same I will define differently. The same example I am taking, but I am giving different mapping here. So here A, B, better I am taking here F2 to differentiate with the examples here. So now I am mapping here 1 to A and 2 to A, 3 to B. Whether this relation, this F2 is function means yes, because here 1 and 2 both are different elements which are mapped with A. So with respect to 1, A is distinct. With respect to 2, A is distinct. So here f of 3 is mapped with B, so it is very clear. So this is also a function. Okay. Now let us define one more with the same example. Okay. So here A, it is B, and here 1, 2, 3 are the elements in A, and A, B, C are the elements in set B. Now I am mapping A with 1 with A and 2 with B, and I am leaving element 3. Okay. So here whether this type of relation is a function means no, because the element in A, that is 3, is not mapped with any element in B. That means the element 3 in set A doesn't have any image, doesn't have any image. So this is not function. F3 is not a function. Okay. Now we'll see one more. Okay. So here again I am taking same 1, 2, 3 ABC. Okay. And the first set is A and B, and one more relation I am mapping. Here I am mapping with 1 with A, 2 with A, 3 is also with A. Okay. So here what will happen means every element in A have image. Okay. So this is function. This is also function because with respect to every element of A is distinct only. Okay. One more example. A, B. 1, 2, 3, A, B, C. Now what I am doing means I am mapping with 1 with A and 1 with B also, and next 2 with C, 3 with B. Okay. Now if you see this, here element 1 have both the images, means 1 is mapped with A and also 1 is mapped with B. That means here the element 1 have two images. F of 1 is equals to A and also f of 2 is also is equals to what? B. So this contradict to our basic definition of a function. So this is not a function. Okay. So these are the examples of function. Now we will see number of possible functions from a set, non-empty set A to another non-empty set. So here take it as a note. Let order of or cardinality of A is M and order of B is equals to N. Then number of possible functions from A to B is n power m. So n power m number of functions are possible from non-empty set A to non-empty set B. Okay. So this is the important point. So now come to the one more definition, that is called domain. Okay. So here we have defined a relation f from A to B and already I have given the definition of a function, that is every element of A is associated with a unique element of B, right? So here first set A is called the domain of the function f. Domain of function f. And set B is called codomain. Okay. Next, one more important definition. This is very important. That is range. So range is nothing but the set of all images of the elements in A through the function f. Okay. That is set of all images of the elements in set A is the range of the function f. So here for this particular function, range of the function A is denoted by f of A. So f of A is equals to the elements, if you take here B, such that this B which is belongs to is capital B. Okay. And see here with the example you will understand everything clearly. So here the same example here I am considering with a different mapping. Here AB I am taking 1, 2, 3 and here it is ABC. Now here I am mapping 1 with A and 2 with B, and here 3 with also B. Okay, so now domain here is A, that means 1, 2, 3. Next codomain is set B, that is ABC. Now what is the range? Range means range of F is the set of all images, means here the image of the function F in elements of A is f of 1 and f of 2 and f of 3. That is nothing but f of 1 means here A, f of B means, f of 2 means here again it is B, and f of 3 means again it is B. So repetition of an element in a set is immaterial, so that A comma B. Okay, so this is the range of the function F, right? Next is identity function. Okay, so F from A to B is any function, or is a function, is said to be an identity function if f of x is equals to x for all elements of x which is belongs to A. Okay, then the function f is called identity function. Usually identity function is denoted with I. Okay, so we'll see one example. So that in the sense, f of x is equals to x means the image of the number is the number itself. That is the meaning of the identity function. F of x is equals to x means the image of the element x is x. That is f of x is equals to x meaning. So here suppose A is equals to, I am taking 1, 2, 3, and B is also equal to, I am taking suppose 1, 2, 3, 4, I am taking, of course, fine. Now here we'll define like this. Here A, B, 1, 2, 3, and here 1, 2, 3, 4. Now I am mapping 1 with 1, 2 with 2, and 3 with 3. So now f of 1 is equals to 1, f of 2, image of 2 through the function f is 2, and image of the element 3 is 3. Okay, so it is called it is an example of an identity function. Okay, next constant function. So f from A to B is any function and is said to be constant function if f of x is equals to A for all x which is belongs to A. That means whatever the element we are taking in set A, if the image of all the elements in set A are mapped with a unique element, a single element, the same element in set B. Okay, then the function is called constant function. That means suppose here I am taking A is equals to 1, 2, 3, 4, and B is equals to, I am taking AB. Okay, so now let us map here 1, 2, 3, 4, and here AB. Now 1 I am mapping with A, 2 mapping with A, 3 mapping with A, 4 mapping with A. Okay, so here whatever the values we are considering in set A, but the image is gives only A. So f of 1 is equals to A, f of 2 is equals to A, f of 3 is equal to A, f of 4 is equal to A. So all these are associating with only single element, that is constant element, that is A. So this type of function is called constant function. Okay, so next, polynomial function. Okay, so let us define a function f from R to R, here R is set of all real numbers and X is an element in R. X is belongs to R such that Y is equals to f of X is equals to A naught plus A1x plus up to so on plus an x power n, where n is non-negative integer, and here all these a1, a0 up to this an are the real numbers, is called polynomial function. Okay, so this is the polynomial function. So here you can take the example, so like f of x is equals to x square, or f of x is equals to x cube, or f of x is equals to suppose to x square plus 7. All these are the examples for the polynomial function. So whatever the value of x, means whatever the real numbers will give, you will get the corresponding real numbers for the functions. So here if you see, I am giving x is equals to 1, then f of 1 is equals to what, means here 1 square. If you give x is equals to 2, then you will get 2 square. 2 square means 4. Okay, so the image of the element 2 through the function f is 4. That is the meaning. So like that we can find the remaining functions. So this is the example for the polynomial function. Okay, next, modulus function. So modulus function means, suppose if f is any function from R to R, or suppose A to B, is said to be modulus function if f of x is equals to mod x for every x which is belongs to R. So here that means mod x means it will convert the negative value to positive value. That means mod x is equals to x whenever x is greater than or equal to 0, and minus x when x is less than 0. So here when x values are negative, the negative of the negative will become positive. So here x is less than 0 means the minus and that negative number becomes positive. So that is only the modulus function. Okay, so we'll see the example and then we'll understand. So here f of x is equals to, suppose mod minus 2. Mod minus 2 means here according to this condition what? Here minus 2 is less than 0. So minus 2 is less than 0 means minus of minus 2 becomes what? Positive 2. That's all. Okay. So here suppose f of x is equals to, when you are taking plus 2. Plus 2 means here x 2 is greater than 0. So 2 is greater than 0 means you will get only 2. Okay. So here modulus function will convert the negative numbers to positive numbers. That is about the modulus function. Next, signum function. Okay. So signum function means here f is any function from R to R, and signum function is defined as f of x is equal to 1 when x is greater than 0, 0 when x is equal to 0, and minus 1 when x is less than 0. Okay. So here this is the signum function. Here in this signum function, the domain is the set of all real numbers. Okay. But the codomain and the range is only minus 1, 0 and plus 1, because whatever the value of x you will give to this function, the output only minus 1, 0 or 1. So these only numbers will be repeated in that function. So here suppose here f of x is equals to 5. When I am taking 5 is a real number, so f of 5, here 5 is greater than 0, so this becomes 1. Suppose f of 0 when you are taking here, f of 0 means here 0. F of suppose minus 5 or minus 15 here I am taking, minus 15 means it is less than 0. So here minus 15 will become minus 1 according to the definition of the signum function. So whatever the value of x we are giving to the function f, but the output are only 1 0 minus 1 based on the numbers. So here take a note that range is equals to minus 1 0 and plus 1. Okay, this is about signum function. Next, greatest integer function. Greatest integer function. So here greatest integer function, f is any function which is defined from R to R, and greatest integer function can be defined as f of x is equals to box x or step x, and x which is belongs to from the real number, the domain here. So here this is the assumed value which is the greatest value integer, is the greatest integer and which is less than or equal to x. Step x or box x is gives the greatest integer value which is less than the x or equal to x. Okay, so here we will see the examples. Suppose here I am taking 5.7. So in this 5.7, here integer part is 5. So this value is 5. Suppose here 5.9. Though here 5.9 which is near to 6, very near to 6. Here you cannot take 6, okay, because here box x is the value of the greatest integer which is less than the x or equal to x. So when you are taking 6, it is 6 is greater, 5.4, 9 is less. So here 5 is only the answer. Though 5.7, 5, 5.1, here 5.1 is also 5 only, it is not 6 or it is not 4. So simply suppose I am taking here minus 0.5 suppose. Now minus 0.5 means it is not 0, it is minus 1, because minus also integers we have, negative integers also we have. So here when you are taking 0, 0 is an integer which is greater than 0.5, minus 0.5. So this 0 we cannot consider. That integer must be greater than, this is less than this minus 0.5. So minus 1. Okay. So this should be greater. The value which is in the bracket is greater, but the output becomes the smallest or the equal number to the value. So here suppose I am taking 10. So 10 is an integer, so there is no doubt here 10 is the 10 only. Okay. So whenever we have the decimal values only, we will consider only integer, and that integer must be less than or equal to the total value. Okay. So this is the greatest integer function. Okay. So next we have quotient function. Okay. So here I am taking let f and g be two functions and such that the quotient of f by g, the quotient of f by g denoted by f by g, and which is defined as f by g of x is equals to f of x by g of x, provided that this g of x denominator should not equal to 0. Then this is called quotient function. Okay. So here when you are taking example, here f of x I am taking suppose here x cube, and g of x I am taking x square. Now f of x by g of x is equals to x cube by x square. So here x, that's all. Or suppose here f of x is equals to, when you are taking here x power 5 and g of x is equals to when you are taking x power 8. Now f of x by g of x or f by g of x, which is equals to x power 5 by x power 8. So here 1 by x cube. This is called quotient function. Okay, so these are the examples of the quotient functions. Now come to the one of the very important topic now, that is also a type of functions, but here from this point onwards all the definitions are very important. So now 1 function. Okay, 1 function. Here I am taking a function f from a to b. Here I will write here, let f from a to b be a function. If distinct elements of a have distinct images, then the function is 1 function. Or we can say no two elements in set A have same image to the function f, then the function is called 1 function. Okay, so in simple words I will tell you, here distinct elements means x1, when you are taking x1 x2 are the elements of set A, when they are different from each other, x1 is not equal to x2, if f of x1, f of x1 means it is the image of the function element x1 to the function f is not equals to f of x2, then the function f is 1 function. Okay, otherwise it is called many one function. Many one function. Okay, so in another words you can say, if two or more elements of set A have same image, then the function is called many one function. Okay, so here just take note. And here 1 function is also called injective function. Injective function. And if number of elements in A is m and number of elements in B is n, then number of possible 1 functions are n factorial by n minus m factorial, where n is greater than or equal to m. Okay, so this is the important condition to define 1 function. Okay, so this is the very important definition. Okay, so here we will see one example, then you will understand easily. Okay, so here f, here a, it is b, and here 1 2 3, and here a b c. Okay, so here I am mapping like this, 1 to a, 2 to b, and 3 to c. Here now distinct elements, here 1 is different from 2, and 1 is different from 3, and 2 is different from 3, and distinct elements have distinct images. Here f of 1 is what? Here f of 1 is equals to a, and f of 2 is equal to what? B. Here a is not equal to b. So you can easily understand that different elements of A have distinct images. So this is called, this is the example for 1 function or injective function. Okay, and suppose here we'll take one more example, and which is not a 1. So here I am mapping here f and a, and here 1 with A and 2 with B, and also here 3 with B. Here this is a function because every element of A have only one image in the set B, but this function f is not 1 function because here 2 is not equal to 3, but f of 2 is B, f of 3 is also B. So here f of 2 is equals to f of 3 we are getting. So this is not one function. Okay, so different elements must have different images, then only the function becomes one function. So this is not the example for the one function. So next we will see one more definition, that is onto function. Okay, and here let take from a to b be any function, and now if f of a is equals to b, that means here f of a means it is the range and b means it is codomain, right? When range is equals to codomain, then the function f is called the onto function. Okay, so that means, in other words, for every element of the codomain B, there must exist one element in set A, that is x, which is belongs to A, such that here f of x is equals to y or y is equals to f of x. If this is possible for every element of the set B, then the function is onto. In other words, for every element of B, there must exist pre-images. Okay, here the first we will take the first set A, and the in first set we have elements, and the elements in set B are called images. With respect to the elements in B, A elements are called the pre-images. So for every element in B, means for every image, if there exists any pre-image, then the function is called onto function. Okay, so here you can define like this 1 2 3, and here a b c, and suppose here I am defining like this a to b, and here it is function f. Now see here clearly, here c is not associated with any one of the element in set A, so that it is not a onto function. Simply it is a function, but it is not onto, because here range is only A and B, but codomain is ABC. So clearly range is not equal to codomain, so it is not onto function. Suppose here 1 2 3, and only the set B have only one element, that is A. Now I am mapping like this. Yes, it is a constant function also, and here here this function is onto function, because here range is set A only, codomain is set A only. So range is equals to codomain, so that this is onto function. And check once whether this function is one function, means no, it is not one function, because distinct elements doesn't have distinct images here. So this is not one function, this is only onto function. Okay, and just take a note here, and here if range is not equal to codomain, if range is the subset of codomain, then f is called into function. Function is called into function if range is equals to codomain only, onto function. Now this onto function is also called as surjective function. Okay, next, number of surjective functions. Here just take number of elements in A is m and number of elements in B is n. Now number of surjective functions from A to B is equal to n power m minus nc1 into n minus 1 power m minus nc2 into n minus 2 power m up to so on minus n minus 1 power m. Here m is greater than n. Okay, so we have to use this formula to find the number of onto functions from set A to set B. Then we will get the answer. So this is about the onto function. Now come to the next definition, that is called bisective function. Bisective function. If a function, if f from A to B is any function, if f is both 1 and onto, then f is called bisective function. Okay, f must satisfies the condition of 1 and also onto, then f is called the bisective function. So here you just take the example. Here example is very simple. Here I am taking a and b. Here a is equals to 1 2 3, and suppose here I am taking x y z. Here I am mapping 1 with x, 2 y and 3 z. Here range is equals to codomain, so here clearly it is onto, so range is xyz and also codomain is b, that is nothing but set xyz, and different elements have associated with different elements, that means every element have distinct images only, so that it is 1 1 also. So therefore it is bisective function. Okay, so here take a note. If f from A to B is bisective, then both the sets A and B have the same elements, So if we are taking elements of set A and element of set B is equals to m, then number of bisective mappings or functions is m factorial. Okay, so this is also one of the important note here. Now next, inverse function. So here first define a function f from A to B. The inverse function, when it is possible, means if the function f is satisfies 1 1 and also onto, means bisective. If f from A to B is bisective, then f is invertible. Invertible means inverse of the function is exist. Okay, that is f inverse is possible. F inverse is denoted from codomain to domain, means f inverse from B to A. Okay, so here for every element of B which belongs to capital B, there must exist at least one element, or exactly one element of set A, such that f of B is equals to A. Here f inverse of B is equals to A means here f of A is equals to B according to this. So here f inverse of B, this B is always subset to the set A. Okay, so this is about the inverse function. Now come to the composition of function. from A to B and G from B to C, B are functions, B2 functions. Then composition of the function is denoted by G circle f of x. G circle f of x, and this is defined from A to C. This is defined from A to C such that G circle f of x is equals to G of f of x. This is true for every element x which is belongs to A. Okay, here G circle f from, 1 minute, I will write clearly. Yeah, now G circle f from A to C such that G circle of x is equals to G of f of x. So now I will take example and I will explain. So here f of x is equals to, suppose x square, and G of x is equals to x. These are the two functions. Now G circle f of x, if you want to find out, it is nothing but what? G of f of x. G of f of x means here f of x value is what? X square. Now G of x, actually we have x, so here G of x square is also what? X square only. So G circle f of x is nothing but x square. Okay, and similarly we can find f circle G of x also. So f circle G of x is nothing but f of G of x. So f of G of x means here x. Now f of x means what? X square. Okay, so this is the example for the composition function. So here, just take a note here first. When f from A to B and G from B to C and H from, suppose, C to D be functions or are functions, then f plus or minus G of x is equals to f of x plus or minus G of x. Means algebraic functions also possible. So next, product of the two functions. If G of x is nothing but f of x into G of x. Already we have seen the quotient of the functions, nothing but f by G of x is equals to f of x by G of x. Okay, now suppose scalar multiplication. When you are multiplying a function with any scalar, that means a into f of x is nothing but a into f of x. Okay, so this is the algebraic functions. So next, come to the one more set, that is partition of set. Partition of a set. So suppose I am taking a set A, let A be any set, is said to be partition of a set. If union of all the non-empty sets is the set A. Okay, union of all non-empty disjoint sets is A, and every set is disjoint. Okay, in simple words I will explain. Suppose here A1, A2, A3, suppose these are the three sets. Now we have, if we can form a set A, this A is equals to union of all the sets A1 union A2 union A3, and these sets A1 intersection A2 intersection A3 is pi, means these are disjoint then set A is called the partition of the set. Okay, so the same thing we will see with examples. Then suppose I am taking set A is equals to 1 2 3. Suppose now I am taking A1 is equals to singleton set A, and B1 suppose A2 is equals to 2 and A3 is equal to 3. Here A, how we can get A means by taking the union of all the 3 sets, and it is very clear that all these A1, A2, A3 are the disjoint sets. There is no common element at all in these 3 sets. So here this A is the partition of set. Okay, so this is the partition of set. Now come to the one more definition, that is equivalence class. Equivalence class. So here first I am taking any relation R. Let R be any relation, and this relation must be an equivalence relation. Let R be an equivalence relation on set suppose X, and equivalence class of an element of X is denoted by box X, and which is defined as like this: X suffix X or this box A, which is equal to X such that X is belongs to capital X, means X is an element in capital X such that X is related to A. Okay, so here we will see one example, and with that example it is you will understand what is equivalence class. Here I am taking integers. So integer means everyone know here it contains 0 and also all positive and negative natural numbers. So 0 plus or minus 1 plus or minus 2, so on. Now I am defining a relation R. Okay, that is X is such that X is equals to A minus B by 4 is equals to K. Okay, or else directly better here I will define like this: A comma B, order pair A comma B, such that A minus B by 4 is equals to K. Right, now this is the relation on I. On I. Now we have to find the equivalence classes. So here in the relation they have given one condition that A minus B by 4 is equals to K. From this we can write A is equals to 4K plus B. Here A is equals to 4K plus B in the sense, when you are dividing A with B, A with 4, it gives some remainder. So these remainders may be which is between 0 to 3. So the possible values of B are 0 to 4. Okay, when you are dividing any number A with 4, possible remainders are 0, 1, 2, 3. Okay, if you have doubt you can check by dividing any number. 5 with 4, remainder here 1, 6 with 4, remainder will get 2, like that. Okay, so A, B, any number here, when you are dividing A with 4, you will get remainder maybe 0, maybe 1, 2, 3, like that. But you cannot get more than 4, 5, 6 because still we can divide the numbers. So here when B is equal to 0, when B is equal to 0, that will completely divides with 4. So here equivalence class of 0 is nothing but, here 0 I am taking here according to the given relation. So 0 comma this B Yeah, one minute here. A comma b such that a minus b by 4 is equals to k. This is our relation, and in this I am taking b is equals to 0. So here you will get a by 4. Okay, so here a comma b such that a by 4 is equals to k. That means here a comma b such that a is equals to 4k. Okay, so here k is what means here integer. So when you are selecting different value of k here, k is equals to, when you are selecting 0 plus or minus 1 2 3 like that, you will get here. When you are selecting k is equal to 0, you will get 0, and when you are selecting k is equals to 1, you will get 4, and here minus 1 means here minus 4. So here plus 2 means your 4 to the 8, like this you will get. So this is the equivalence class of the 0. Okay, now come to the next equivalence class of the b means here one more element is possible here, what 1. So 1 means a comma b such that a minus here already we have got directly equation I am taking here. A is equals to 4k plus b. A is equals to 4k plus b. So here a comma b such that a is equals to b value. Now b value is what? 1 I am taking. For clarity we will write like this. B is equals to 1 I am taking. So here 4k plus 1. So here 4k plus 1 means here take k value anything. So when you are taking k is equal to 0, you will get 1. K is equals to 1 when you are taking, you will get 5. K is equals to minus 1 when you are taking here minus 3. So like this you will get. Next equivalent class of 2 means here a comma b such that a is equals to 4k plus 2. So similarly, when you are giving the random values of k as integer, you will get here k is equal to 0 means you will get 2, k is equals to 1 means you will get 6, k is equals to minus 1 means here you will get minus 2. So this is the equivalent class of 2. And equivalence class of 3. Equivalence class of 3 means here again a comma 3 you can write, or a comma b, here it is fine. And a is equals to 4k plus 3. Now here k is equal to 0, then here you will get what? First when your k is equal to 0, then you will get here 3. Okay, so here 3 you will get. When you are taking k is equal to 0, 3, and when you are taking k is equals to 1, you will get 7, and minus 1 means here minus 1. Okay, so this is the equivalence class of 3. Now if you try to find out the equivalence class of 4, that means here when you are taking b is equals to 4, again it will repeat. That means here 0 will come. So here no need to repeat that. So we will stop up to the 0, 1, 2, 3 only. So these are the equivalence class of the set A under the relation R. Okay, so this is the solution. Now here you have to understand one thing. Here we have a note here. If A is belongs to the equivalence class of A and B is belongs to the equivalence class of here A is belongs to the equivalence class of B. If an element is belongs to equivalence class of B, then the equivalence classes of A and also B both are equal. That's what I said here before, that when you are taking 0 and also 4, it gives the same. Okay, so if A is an element of the equivalence class of A and A is element of another equivalent class, then both the equivalent classes are equal. Okay, and here either both the equivalence class are equal or both are disjoint. Okay, so these are the two notes which are important in advanced classes. Okay, so that's all about the function. So thank you everyone, thank you for watching. So thank you very much.